Okay, good morning, everybody. We're continuing the session on measuring and monitoring. My name is Ramon Hansen, and we'll have 3 talks now before the coffee break. And the first speaker, now I lost, where are you?
Yep.
Oh, sorry. Dr. Chen from Taiwan, and this will be on gravimetric data, right? So the floor is yours.
Where is the pointer?
It works. You just need to keep it pressed.
Okay, I'm Chen, and today I'm talking about the assessment of the potential recharge lakes by absolute gravimetry in the regions of the severe lens subsidence in Taiwan. So I'm talking about the gravimetry or the gravimetry data that wasn't mentioned in previous keynote speak. Maybe you are not very familiar with this one, but I will try to make a brief introduction about this. So the purpose is quite straightforward, that we are going to assess the potential recharge lake within the surveillance subsidence regions, because we would like to recharge the groundwater just directly in the lens subsidence region, not from the proximal band to the middle band. That will be a lot of the clay aquifers. Let me see. Okay. So it's the central Taiwan. There's a social aerial band, and here's the proximal band and the middle band and the distal band. So in 2021, the middle of our audio band, they experienced a severe lens subsidence here, and along the hydrogeological profile here, we set up several gravity sites in the blue circle along this profile. So we will look at this profile here, from the DHES here to the west to the HYCR. And you can see that in this year, the lens subsidence is approached to 7 to 8 centimeters in a year. So what we're going to do is that we're not going, because we know that if we increase the groundwater level here, groundwater can be transmitted to the middle band. But I'm looking for directly inside the lens subsidence region, that maybe it could be some regions that with some unconfined aquifer, then maybe we can apply a recharge lake or directly inject the groundwater here. So it's much more efficiently to inject water directly in the region here. Hello? How can I move on?
Okay, maybe use the enter button.
Okay, yeah. That was here. So the hydrogeological profile here. And so this is the profile that made it like 2 decades before from now. So they show that might be some small regional unconfined aquifer here that could be stored groundwater. They could be applied for the recharge lake. But we don't know how's the ability here. We just saw that, there's some region here with some sand here, different from the clay. And we see that in 2021. So usually in our subsidence region, that from the dry season, this is the GPS data here for several sites in blue. So in 2021, if you look at the green and the blue ones, So from May until May, the height change could reach about 10 centimeters. And after the rain season, the ground surface rebound to about 6 centimeters. And after the rain season, it's going down again. So our ground surface looks like this. We face the subsidence and rebound because of the rain. And after the rain season, it's going subsidence again. Okay, so if you have a chance to look at the gravity data for the time-lapse gravity, usually after we removing the environmental corrections like the tides or something else, it remains in two components. So one is contributed from the deformation, and the other one is from water change. So if you, like us, we collocate our sites to the GNSS station, so we could have a deformation here, and the coefficient here we use is 2.0. So you have the deformation here. So if you subsidence for 1 centimeters, your gravity value is going to be increased for 2 microgauss. There's some different argument about this coefficient, but usually it ranges about 1.8 to 2.2. But we just take 2. It's quite easy here. So in these two components, if you remove this one, so the other one is the groundwater component here. And more of them, if you look at the like GRACE, some of the space satellite, they will talk about the equivalent water height. So you may know that how many gravity change here, and you can refer to how many groundwater you have remaining or difference from the last time you measured. So, but in this case, we're using the ground-based gravimeters, so we have to talk about the sensibility of the region we are looking for. So there's a rule of thumb that if your groundwater depth is like this, and in the cylinder area that the radius about 10 times your depth, so this area will be the more sensitive region that you are looking for. So there's a case here. If we got a 1 microgauss change, so if the RP, the radius is about 250 meters, so it's about 4,600 tons of water here. So it's if you are in somewhere that only have confined aquifer here, so you can see that the contribution, no matter how many groundwater level you detect, maybe 10 meters, you only got very, very little about the groundwater change from here because of the storage coefficient here is very small. Then you can almost show that the gravity change you look is how many deformation you got. You just divide it by 2. But in our case, we're looking for if there's somewhere there's a clay dominated area, which is supposed to be only the confined aquifer. But before looking forward, that I will show you that. So if you in purely unconfined aquifer, you will see that the black dot is the gravity change. It's very consistent with the groundwater level change. In this case, we put it in 1.5 years. So you can see the groundwater level in blue is very consistent with the gravity change here. So if you can only like measure for 4 times in a year, you can see that it's very clear that the groundwater level is going down, then your gravity change is going down. Also, the groundwater level is moving up, and you get an increase of the gravity changes. So before I will talk about the storage coefficient in the typical test. You will find out if you are somewhere in the heterogeneous aquifer, you will find out in a site like this, it's just about 25 meters to 25 meters. you found your test result will look like this. So the range here in the vertical way, you will see that it becomes an uncertainty that in this small region, you will have the result like this. It could be from 0.1 to 0.2. So it's 2 times. So when you are estimating how many groundwater remain in your sensitive regions, you got uncertainties like this from several times to 10 times if you use the typical pumping test result. There's another thing to mention that from the typical test results, there's a different method to apply to the curve fitting to the your observation results. So from Newman to the lattice present result here, you can also find at the same single well, you may have a different result here. So it makes a lot of uncertainty here if you consider to use the storage coefficient from the typical pumping test. We have proved that if you use the gravity-based value of the estimated specific yield or the infiltration coefficient, percolation rate, you can use gravity to determine these 3 kind of the important coefficient you need in your model when you are talking about if you are looking for the recharge lake, artificial recharge lake. Okay. So again, this one is the deformation here, and this is the gravity change we detect here. So suppose you are in the only the confined aquifer, where you establish a gravity change. You're supposed to have a gravity change like this. Because of the subsidence, your gravity change is moving up. And because of the rebound, it looks like this. And when the subsidence keep going, your gravity change might increase like this. However, we found that in here region, we saw the gravity change is moving up and up and up. And then even after the rain season, the gravity value is going down. So let's look at that. We step inside the subsidence regions. So because of that, there's also not only the subsidence, it also consists of the groundwater change here in this region. It means that it's not just confined aquifer here. It should be some of the unconfined aquifer here that we may use for looking for the recharge lake, the potential recharge lake. So we can, by the formula there we talked previously, we can have a separate for your gravity changes here. So we look at the side STES is right here. So the profile shows there is an aquifer 2 here, regional unconfined aquifer here, and there's another one here for the STES and JJES. So in this case, before the rain season, we can see the gravity contribution of the gravity almost dominated by the subsidence. There's only a little bit groundwater left here because irregularizations are pumping here. But after the rain season, you can see that, the gravity is still increasing, but the subsidence remains, but there's still stored a lot of groundwater here. It means you can still pump out the groundwater if you like, because the subsidence is only remain in this scale. But if you compare to the two sides here, we can see that if you are looking for a better recharge lake, this one will be much better because it can remains more groundwater here even at the rainy seasons. And the patterns is more look like this one in the pure unconfined aquifer, that when the groundwater level rise and the gravity values increased. if you look at a geological map, there's a site called TKJH. You see that in the year 2016, there's a lot of rainfall in these years. So the graph has increased because a little bit about the subsidence years, and the groundwater is in the negative terms. It means that relative to the first time we measured, the groundwater is lost here. But in 2021, the groundwater even lost much more than the 2016s, and also even the subsidence looks like the same, but it transfers the total gravity change value to the -1, and so on. So in these 2 years, the total rainfall are almost the same, but it remains more groundwater here. So it's a case in this region. So it's quite consistent with the hydrological profile that here is the clay dominated, not as the IUA 1 or IUA 2 that may have some unconfined aquifer here. Okay, so not just the gravimetry, if you're looking for how large it could be of your original unconfined aquifer, we might join with the ERI techniques. You may know the boundaries or the possible area of the unconfined aquifer where you are for your management. So this is the case we join with the ERI. Okay, in summary, that if you have a gravimeter and you set up at the subsidence regions, we're looking for significant gravity changes. I mean significance that usually 2 to 3 times more than your uncertainty of your gravimeters. You can show that, oh yeah, there's other than the subsidence, here might be some unconfined aquifer for use for maybe establish and recharge lake. And so the gravity-based methods for IUA identifications is non-instructive and require little support operations. It means cost-effective. So usually we are applying an instrument that we should consider first that is it cost-effective. If it is, then it might be a good technique to integrate it. And also, not just because we can only censor about the region in several hundred meters to n kilometers. So if you're looking to know the area or the boundaries of your unconfined aquifer, try to use the ERI to join with the older techniques here. Thank you.
Thank you very much, Mr. Chen. Yeah, we're running a bit behind time, but I think there's a good moment for this discussion. Shimon.
Soil moisture, can it affect, how much it affects your measurements?
Yeah, there's usually at what paper was sold that usually it takes 1 to 3 microgauss. Usually, because there's some in Europe groups, they're using the superconducting gravimeters from some observatory sites. They simulate and they also estimate of the values. It's just around 1 to 3 microgauss, usually in a year. Yeah, so if your gravity change is significant, which means it's larger than like 5 microgauss, we should consider that there is some unconfined aquifer there.